Okay, in this video we will talk about the seismic isolation of the building or the base isolation of the building, and we will subject it to the nonlinear time history analysis. Now, before performing the modeling, why base isolation is important? So, just to demonstrate it, you can see that when the foundation or the structure is fixed with the ground, all the acceleration, displacement and the energy is transferred to the entire structure, and the columns and beams and the slab has to dissipate that energy. However, when you isolate this structure at the base or at some appropriate level, the energy will be most of the energy will be dissipated by those isolators, and the elements, the beams, the columns, that will not be subjected to the same amount of energy that they were sent otherwise. Okay, so this is a comparison of shear force demand in this structure. As you can see that the demand is much greater in the fixed base structure as compared to the isolated structure. Okay, and here is another comparison of the base shear. In the fixed base building, you can see that the maximum base shear is 445 kips. Alright, however, in isolated structure, the maximum demand, the maximum base shear is only 68 kips. So the ratio is about 6 to 7 times. The isolated structure reduces the energy demand about 6 or 7 times on the structure. So the structure will be much more economical as compared to the regular structures. This is the base shear with respect to the bottom story. Let me show you which one is C. This is the bottom story. This is joint 13, this is joint 14, and this is joint 15 at the top story. So I have made a comparison of joint 13 and joint 15. Since in the fixed base structure the joint 13 is fixed, alright. However, in the case of isolated, the joint 13 is not fixed and it is attached with an isolator. So joint 15 will be presenting the top story, and joint 13 will be presenting the bottom story. So this is the base shear with respect to the bottom story. In the fixed base structure, the joint 13 is fixed, so you can see only a single line, the red line, where the maximum value is 445 kips. However, in case of isolated structure, the demand is only 68 kips. Similarly, when you plot it against the joint 15, which is at the top story, you can see the difference. Alright, the energy is much more dissipated in the base isolated structure. And this is the joint displacement of top and bottom stories. See, the joint 13 displacement is green and joint 15 displacement is red, but in fixed building there is no relative displacement of joint 13 because it is fixed. However, in case of isolated building, joint 13 and joint 15 both are, you can see both yellow and green colors in this graph, right? So there is a small relative displacement between joint 13 and joint 15, and because of that the demand on the structure reduces. Now let's begin with our example building that we have to model. Basically, it is a steel frame with concrete slab, which means that the slab is made of reinforced concrete structure, and the frame, the beams and the columns, they are made of steel sections. The height of each story, the structure is basically a two-story with the two bays in each direction. The height of each story is 12 feet, and the width of the bay is 30 feet in each direction. The top slab is 6-inch thick concrete slab at the roof, and for the first and second floor the slab is 10-inch thick. And it says that provide diaphragm constraint at each level to make all diaphragms rigid in plane. Alright, we have to make them in plane rigid. We will discuss that later in detail. The steel properties are given. The beams are W24 by 55, columns are W14 by 90. The isolator properties are the vertical stiffness or the axial stiffness of the isolators are 10,000 kip per inch. The initial shear stiffness in each transverse direction is 10 kip per inch. The shear yield force in each transverse direction is 5 kips. Ratio of post yield shear stiffness to initial shear stiffness is equal to 0.2. The loading is also given. At the roof, dead load is 75 psf and the live load is 20 psf, and at the floor the dead load is 125 psf and the live load is 100 psf. And the time history, apply this already available time history data in the SAP database in the x direction and this one in the y direction simultaneously. Each time history is given in units of centimeter per square second. There are 3000 time steps at an equal spacing of 0.02 second for a total of 60 seconds. Alright, so this video will demonstrates you the modeling of link elements, the base isolation or the seismic isolation, the diaphragm constraint, how to apply them and what are their uses, the Ritz vectors, dynamic analysis, mode shapes, modal nonlinear time history analysis, etc. Okay, so let's begin with the modeling. We will start with the new model. Alright, so just click on the new model, and when your computer is ready, the window will appear. Now change the units to keep fit, select the 3D frames. First of all, remove these restraints because we will isolate them. The number of base is 2, story height is okay, this is 30 and this is also 30. Now for the beams and columns, click this plus button, select import new property, steel is okay, press I and import the sections. Right, now the required sections are W14 by 90. So go to the 14, scroll down and select this section W14 by 90 and W24 by 55. Alright, click OK and you have imported both the sections. You can check their properties by clicking the modify properties. Right, okay, so the beam was W24 by 55 and the column is 14 by 90. All other details are okay, so click OK. Now I have defined the columns and beams. If you want to see them, you can just click the sections in the frames cable standards area and you can see the beam is W24 by 55 and the columns are W14 by 90. Alright, now we need to define slab because we will go step by step. Shell is good. Add new section, give it a name of roof because we have to define two sections. The roof has the material properties, okay, it's a 4000 concrete. The roof thickness was 6 inches, which is equal to half of the feet, and all other details are okay, so click OK and add new section and give it a name of floor. The 4000 psi concrete is okay. The thickness was 10 inches, so put 10 inches. Click OK. We have defined two area elements. Now we have to define the isolators, but before that convert your units to kip inch, because if you remember in the given data all the units were in kip inch. So click this link support properties, add new property, make it rubber isolator, give it a name of rubber 1, whatever name you want to give it, you can give it. The mass is 0.001. Click U1 and click modify show. The axial or the longitudinal effective stiffness was 10,000. Click OK. Click U2 and click nonlinear. It is in the transverse direction. Click 1.5, 10, 5 and 0.2. Right, all the properties are per the given details. For example, if you see here, the 10,000 was the axial or longitudinal stiffness, 10 kip per inch is the shear stiffness, shear yield force is 5 kips and 0.2 is the ratio. Right, so this is what we have put it, 10, 5, 0.2. Alright, Now the same details to be provided in another transverse direction, 1.5, 10, 5 and 0.2. Alright, so we have defined an isolator called rubber 1. Now we have to define the load patterns. So that is already there. Define another load which is live, add new pattern and click OK. Now we need to define the area sections. We need to assign them. So select this quick draw area element and make sure that the floor is highlighted here at z is equal to 144 inch, or if you want to change the unit it will be 12 feet. Okay, so click in all the areas, go to the top floor and select the roof and assign them. Okay, so now we have assigned the area sections. Go to the z is equal to 0 and we have to draw the isolators. So go to draw one link, one joint link, and rubber 1 is highlighted. Okay, so click at all the joints, 1 2 3 4 5 6 7 8 and 9. Okay, so you can see in the 3D model that all the 9 joints have been assigned with the isolators. Now we have to assign the loads to these floors. Select the entire uh, view by windowing it and go to the assign area loads, uniform shell. The dead load given is okay, let me change the unit to pounds for convenience. The dead load given was 125 pounds, right? And let me change the units here as well so that I don't have to do it all the time. Now select the previous selection and assign area loads and live load. Select the live load. The live load is 100 for the floors. Click OK. Now I have assigned both the dead and live loads to z is equal to 12. Now move up and select it and go to the assign area loads and uniform shell. Select dead. The dead load is 75. Go to the previous selection, assign area loads, uniform shell, and select live, which is 20 psf, right? So we have assigned all the loads. Change the unit back to the keep fit. Select the undeformed. Now we have to move floor to the base as well, because if you can see there is also a floor, a diaphragm at the base level as well. So go to the z is equal to 12, select all. Alright, go to the edit, replicate, and put minus 12 because the story height is 12 feet, so minus 12. Click OK and it is replicated here. Alright, and the loads are already applied to it. Now we have to make the diaphragms rigid, because if you remember, it was given here that provide diaphragm constraint at each level. Now what are diaphragm constraints? So a diaphragm constraint in SAP, it causes all its constraint joints to move together as a planar diaphragm that is rigid against membrane deformation, right? So this constraint can be used to model concrete floors in building structures which typically have very high in plane stiffness. So basically you want to make the slab stiff in the in plane direction, right? And you don't want any relative displacement of the slab within its elements. At the constraint axis, the constraint equations will be written for a diaphragm in a plane perpendicular to the selected axis. For example, first let me take you to the diaphragm. We will start from the top. Select all of them, go to assign, joint, constraints, and see, instead of body select diaphragm, add new constraint, and this is the constraint axis that we were talking about. So let me take you back to the constraint axis. The constraint equations will be written for a diaphragm in a plane perpendicular to the selected axis. For example, if the z axis is chosen, this constraint is equivalent to a body constraint in the same coordinate system with translations x and y and rotation z chosen. Okay, so let me take you, for example, this is your translation in x direction, this is your translation in y direction. So when you move your element or your structure in x and y direction, it will definitely rotate about the z axis, right? So that's why a translation in x and y and rotation about the z axis, right? So it is equivalent to a body constraint. What is body constraint? In body constraint, all its constraint joints causes to move together as a three-dimensional rigid body. But in diaphragm constraint, only the in planes properties are made rigid, and it will act as a unit in the in plane direction, not in the out plane direction. Okay, so this is the in plane direction, and this one is out of plane direction. So it will act as rigid in this direction and in this direction, right, but not in this direction. So this was the purpose of the diaphragm constraint. So I have to put z axis because of the explanation I just presented to you. I will type here as a roof, right? Click OK. So the constraint is applied. Now go to the z is equal to, okay, give it some time, go to z is equal to 12, select all of them and assign joint constraints and diaphragm constraint, add new constraint, give it a name of second floor, right? Z axis is okay, click OK. OK, and constraints are applied. Now go to the bottom floor or the first floor and go to the assign, joint, constraint, diaphragm, add new constraint and give it a name of first floor, right? So the constraints are applied to all the floors. Now we are done with the modeling of this structure. If you want to see the structure, fill the objects. See, this is your structure, right? Now we have to define the loading for this structure, the time history analysis, and for that let's go to the define menu, functions and time history. Select the choose function from the file, add new function, click the browse, go to the time history function, select all files, and LACC North 1 was required in the problem statement, give it as the name of LACC 0, right? Header lines, okay, let me first show you the file. Click on the view file and it will open in the WordPad, and you can see that the top two lines are not as a data lines. Also there are 8 points on each lines, 1 2 3 4 5 6 7 8, that are the data points. So for this reason I will select that header lines to skip are 2 and number of points per line are 8, and the value at equal intervals is selected as 0.02. Alright, uh, here I will select the free format. Now what is the difference between free and fixed format? So in the time history function definition, the program reads the time history function file as first it skips the specified number of header lines, which we mentioned as 2, right? Next it checks if a dollar symbol is at the beginning of any line. If yes, then it will skips. If no, then it will read that line. If the line is blank or when the end of the file has been reached, the program stops reading and closes the file. Okay, so this is how it reads the file. Now format type, either free format is good or the fixed format is good. In free format items on the lines can be separated by spaces or tabs. So you simply put a tab between two entries, and it is very simple format. But for a fixed format type, specify the number of characters per line. So first you have to specify the number of characters per line, then each item on the line is assigned the same number of character spaces. So the character spaces should be same. The third thing is that program begins counting the spaces after it skips the number of prefix characters specified in the prefix characters per line to skip added box. Okay, so this free format is much more easier than this fixed format. Therefore we have used this free format, and click the display graph, click OK, and go to the modify. Okay, now we have to add new function because it is in the one direction. In the other direction we have to define another one. So give it a name of LACC90. Alright, and browse the file, make the type, and select LACC North 2, click open, and make the same things, two header lines to be skipped, 8 and 0.02. okay, and click OK. Now let me close them and reopen it. Okay, so define functions, time history, LACC 0, modify. So this is your time history function of the earthquake in 0 direction. Okay, and this is your time history function in the perpendicular direction. So we have defined both of them. Now close this window and come to the load cases. Alright, in the load cases, first highlight this model option and modify. Click modify. The model case name is okay. Here it is selected as model. Okay, now please note that for the eigenvectors the detail is different. We will go with the Ritz vectors, right? Change this number of modes to 30. It is up to you. You can change it, you can make it as much number of modes as you want. Okay, and the other details are that you can select this load pattern. It is okay. The dead is okay, and click add. Now select the Excel UX, click add, select UY, click add, and select link all and click add. Now we are good with the model analysis. Click OK to close it. Now we have to add new load case. Okay, so in the new load case, which will be our gravity load case, select type GRAV as its name. Alright, in the load case type, select time history, and in the time history analysis type, select nonlinear, and in the model load case, model is okay. In the loads applied box, select the load pattern which is already selected. The dead is good, and here select this file ramp th time history. Okay, and click add. So it has added your dead load with this function. Alright, the number of output time steps 100 is good, and output time step size 0.1 is good. No need to change any other detail, and click OK. Okay, now add new load case. Here change the name to LAC. Alright, and then change the load case type to time history, just like previous. Select nonlinear, and do not select the 0 initial condition, but continue from the gravity. Alright, in the loads applied area, you have to select the load pattern as XL U1 LACC 0, and in the scale factor you have to type 0.0328, because in the pound in the feet second, 1 feet per square second is equal to 0.0328 g, right? So this is the value of g. Click add, select u2 and 90 and click add. Here you have to type 3000 because it is required in our data, and type 0.02. Alright, now in the other parameters, click on the modify show, make sure here it is 0.05, good. For the mode 1, type 0.02 and click add. Mode 2, it is 0.02, click add. Mode 3, it is 0.02 and click add. Okay, so now we are good. Click OK. All other details need to be same. Click OK. Click OK. Now we are done with it. You just have to save this file. So click on this save and save it at an appropriate place wherever you want to save it. For instance, I am saving it where the name I am giving it is 5. Click save and now run analysis and run for all these options. Okay, so run now. It will take some seconds to run the analysis, and after that you can check it. The analysis is running. Once it is completed, it will show you. See, the analysis is completed. Alright, so as I mentioned at the beginning that the joints, this is z is equal to 24, this is joint 15, and at z is equal to 0, this is joint 13. So go to display, go to, I have selected both the joints by the way. Okay, show plot functions. Alright, and see joint 13 and joint 15 are highlighted. First of all, select the load case as LECC. Click this define plot function. Here select the joint 13, go to modify, select uy instead of ux, and displacement is good. Okay, click OK. Similarly, click the joint 15, select modify, displacement is okay, you select uy instead of ux, click OK. Now come to this area and select this add base function, right? And once you selected it, click to the add plot function. Here select the base shear in the y direction. Okay, so once you are done with it, click OK. Now here select joint 13 and joint 15 and add them, and you can click this display button to show the relative displacement. So see, this is the same graph that I presented to you at the start. See, this one is for the isolated building. Similarly, you can remove both of them. You can check for the base shear, right? Select base shear and you want to see it with the time and select display. So this is your base shear graph. Alright, so similarly these are the results. Also you can check other results as well. For example, here if you want to see the deformed shape, you can check it for any of the given loadings. Start animation. See, this is how similarly for the modal analysis you can check it for the model. Okay, start animation. This is for the first mode. See, nothing is happening, the isolators are moving but the structure is intact, so that's why we used isolators. I hope you have learned the things, the techniques to model the isolators as well as to define the time history analysis. All the points that we discussed in the presentation. For example, here the link elements, you have learned them, the base isolation, the diaphragm constraint, Ritz vectors, dynamic analysis using the modal analysis, as well as the time history analysis, model nonlinear time history analysis, and the mode shapes. Let me show you again the mode shapes. For example, this is the mode 1. Now click it again and select mode 2 and see how it will move. See, this is the movement in the mode 2. You can select higher mode, mode 3. See, this is the mode 3. You can check it for any of the mode. For example, mode 11. This is how, see. And if you want to check it for the check it in the 3D, so select it, model, and for example select for the mode 6 and start animation. See, this is how it will be in mode 6. And you can check it for other modes, for example mode 8. See, it is twisting, the floors are acting in opposite manners. It is acting, it is rotating clockwise, the other one is rotating anti-clockwise, and vice versa. So this was all about the mode shapes, and you can learn the mode shapes in the structural dynamics course. And I hope you have enjoyed this video and you have learned a lot of things. And if you have any suggestion, kindly mention it in the comment section. See you in the next video. Thank you very much.